Welcome back. This is Lecture 3 of Systems Design 522, the Fundamentals of AI, taught at the University of Waterloo in the fall of 2023. And I'm Terry Stewart. What's on the books for today? We're going to talk about clustering. So the last two lectures have been all focused on supervised learning. And now I want to sort of take a step back and look at unsupervised learning. So this is a situation where all I've got is a bunch of input data. Nobody has labeled this data. Nobody's told me what it is. All there is just a bunch of data. Please do something with it. And the particular thing that we're going to focus on doing with that is, can you organize this data somehow? Can you like put it into groups? I give you a bunch of pictures, and I want the system to, like, without any sort of background knowledge, sort of divide these pictures somehow. Whether or not they get divided in terms of dogs versus cats, that's probably not. I mean, there's all sorts of other ways of dividing pictures. It's going to find some ways of dividing these pictures, or dividing these input data. Okay. We're not going to be dealing with images, just because images have a lot of data points. So as sort of a simple example, let's look at something like what we see on the right here, where we've just got each of these blue dots is a different data point. Each data point has two dimensions, x1 and x2. That's what we've got there. And if I just plot the data, a person looking at that data pretty quickly says there seems to be three groups of data there. There's data here, there's this here, there's this here. How are we doing that? Can we do something like that in an automated way with an algorithm? That's sort of our goal here. Okay, so what sort of approaches are we going to take to make that happen? Well, since my background is cognitive science, or well, originally engineering, then cognitive science. In any case, one way to go to is, well, how do people do these sorts of tasks? What are theories about how humans categorize data? And so you know, if we want to look at how people group data together, there's all sorts of history of people studying how people group data, or especially visual data, stimuli that's coming in visually. There's this whole Gestalt visualization ideas where, hey, if I give you a bunch of dots like that, people tend to group that into, you know, if I told you to just organize that data somehow, it's a little bit more common for people to say that is 5 separate columns, each of which has a bunch of dots in it. That's somewhat more readily accessible than people saying, oh, that's actually 7 rows, and each row has 5 dots in it. Right? So why are people doing that? Something to do with distance, perhaps, so that there's definitely a smaller distance this way than this way. Although that gets changed a little bit. So if I modify the stimulus a little bit, make them the same distance apart, but then match colors, now people are sort of, that one, that's 6 rows of 6 dots. Is sort of a more readily available statement than that's 6 rows of, or 6 columns of alternating dots. The point out of all of this is there's some sort of underlying similarity measure that is going to be important here, and that this similarity measure is going to be some sort of pretty generic thing. It doesn't just have to be distance, or if we want to think of it, if it's distance and color and shape and all things, if we put all of those in some high-dimensional data, then perhaps we could call that sort of distance in some high-dimensional space. But this issue of distance and similarity is going to come up over and over and over again. All right. So keep that in mind. And then the other thing that I'm going to sort of just toss in here as a little bit of extra bonus is just to point out that the approaches that we're going to look at today, or at least 2 of them, when people examine human category formation, there tends to be a bunch of different ideas, and we're going to sort of explore 2 of those in algorithm form. So when people study human categories, one idea of what it means when if I'm thinking about birds, what the hell does it mean for me to imagine what a bird is, or what is my mental representation of a bird? One particular idea that's pretty common out there is, oh, I have some sort of mental representation of like the canonical ideal bird. And then if I see a new thing, then I can sort of measure some sort of similarity between that new thing and that canonical ideal bird that is in my head. Okay. And so that becomes a nice sort of efficient way of encoding this information. I can just say, oh, okay, all right. There's some sort of, birds are about this size, generally found outdoors, a bunch of sort of general features, maybe of those somehow encoded in some sort of numerical method. And then we have to have some sort of similarity measure when I get this new item comes in, and then I say, oh, that's a bird. So that's sometimes referred to as prototype theory. It's the theory that we represent things based on prototypes. I have a canonical prototype of what is in my head. That's one approach. Other approaches that people take for representing human categories is exemplar theory. So this would be, hey, maybe I don't just represent one ideal bird. Fine, that's a nice, efficient way to do it in computers, but maybe what people do is you just memorize all of the examples that you've seen of that category. Lots and lots and lots of examples, maybe not all of them, but just lots of examples of that category. And when I get a new item, I just say, oh, is it similar to any of them? So I've seen many different types of birds before. Is this new bird that I'm seeing, is it similar to any of those birds? Right. There's a bunch of interesting experiments to sort of tease apart those ideas. There's fun experiments like people's canonical idea of spoons seem to either be small in metal or large in wooden, but you don't get the sort of the other combinations. You don't have it's much less common for people to think of a small wooden spoon or a large metal spoon. And so that makes both of those end up, or that sort of argument ends up being pushing you a little bit over to exemplar theory. But then, of course, there's arguments both ways, and clearly we can't represent all of them. So yes, there's other theories that sort of do a merging of the two and multiple prototypes or things like that. So both of those two theories that I'm going to talk about, we're going to talk about algorithms today that sort of somewhat match into those ideas. We're not today going to talk about the third class of things that people talk about for human categories. It's the other approach in cognitive psychology when people are studying these sorts of things. Instead of prototype theory and exemplar theory, there's also theory, which is the theory that what it means to have the idea of a bird is you have a bunch of like rules that say, oh, a bird is something, it has wings and it knows how to fly, except for penguins. And, so you have some sort of explicit set of rules that say exactly whether or not it works. Anyway, that sort of approach to categories, we might get into sort of at the end of the course when we get back into sort of some of the extra topics. We'll talk about good old-fashioned AI and things like that. There was much more sort of rule-based and expert systems and that sort of thing. Today we're going to focus on those first two approaches. All right. So let's start with a prototype-based method. So what do we, again, for the prototype, the way I want to represent these categories is I'm going to have sort of a canonical sort of best case of that category. And if we look at these things, it's like, okay, well, that would be the best example of this one. And then this, somewhere around here, would be the best example of this one. And somewhere down here would be the best example of that one. But I want that to be done automatically, not just by me moving my mouse around and looking at the data. So I need an algorithm that'll do this. Okay. So here's what we're going to do. All right, we're going to have some prototypes. First question. We're going to start with some prototypes. How many? Do I want 4? Do I want 7? Do I want 3? How am I going to know this number? For now, we're just going to pick it, and then we'll talk later about can we figure out whether or not we've chosen a good value. So we're just going to pick it. We're going to choose how many. And now we're going to start our algorithm with our initial guesses for these prototypes. And what are we going to do for that? Well, let's just sort of randomly pick 3 of the examples that we have. Okay? All right, I've randomly picked 3 examples. Okay, those are probably pretty bad prototypes. Let's adjust these prototypes somehow. How are we going to adjust these prototypes? Well, if we have these initial prototypes, these things that are divided my world into 3 categories, well, let's actually do that. For each of these points that's on the screen there, we can, well, okay, this point here is clearly part of this category because it's closest. And this one's part of this category because it's closest. This one's part of this category because it's closest. These ones here, I guess, are part of this category because that's closest. So we just go ahead and classify all the data points. And you know, since this is based on distance, and for the purposes of this, I think everything I'll do today, I'll use Euclidean distance. Lots of other distance measures are possible depending on your data, but we're going to just use Euclidean distance. And that's going to mean that everything on this, over this side of the line, is going to be closest to this, and closer to this than that. So everything up here is going to be in this category, everything here is in this category, everything down here is going to be in this category. All right, fine. We've done this for these randomly chosen categories. Looking at those, though, those prototypes that we have now aren't very good examples of that category. Right? Like this X is over, you know, like this prototype is here, but pretty much all the data in this category is over here. So let's update this prototype. And what we'll do to update it is we will take all the data points that are classified with, you know, or that are closest to this prototype, or so are classified as this item. Take all the data points that are closest to that, and just take the average. Right? That'll take us to around here. Do the same thing to this, and do the same thing to this. Now if we do that, all right, that's going to give us new prototypes. All right. Now interestingly here we have a prototype that looks, I mean this particular prototype looks nothing like any of the data in the category. So for the moment it's kind of a weird prototype, but fine. And then what we're going to do is we're going to say, all right, well now we've got new prototypes. Let's repeat the process. There, update, and we repeat it a few times, and we should get something centered there, something centered there, and something centered there. All right, nice simple algorithm. So this is called the k-means algorithm. K because we choose k prototypes, and means because we're just taking the mean of everything that gets categorized in there. There's of course tons of variants. You could do k medians. You could do anyway. But this core idea of just pick some prototypes and repeat is sort of, this is pretty much the first most common method for doing any of this sort of just immediate classification or category. So what's that look like on actual? We're actually running the algorithm rather than just me drawing X's on PowerPoint or on slides. So again, here we are. There's my prototype. Here's 3 randomly chosen prototypes, and we're filling, and I'm coloring them based on what they're categorized as. And that's just the initial randomly chosen. And now I do one step of the algorithm. All right, and so that's, you know, this one moved to here, this one moved to here, this one moved to here. Iterate again, and even just after just 4 steps, we're getting pretty darn good groupings into these 3 categories. Okay. So one thing we might want to do while running this algorithm would be to have some sort of measure of how well is this working? Is this is this working at all? How can I quantify how good these categories are? Maybe is a way to put it. Okay. And one sort of possible, if I want to categorize how good these categories or these clusters are, one thing I could do is I could say, all right, what I want out of these categories is for the prototype to be a point that is nearby all the points in that category. Okay, so I could just compute the sum of the distances from every point to its category's prototype. Okay, all right. Okay, so this is this what I've written down here. So this is the xi, that's a particular data point. ck, that's going to be the category, the prototype, the whatever, the x value for the prototype that it is closest to. I'm going to compute that distance. I'm going to add that all up for all of the points within a category, and then also all over the categories. Divide by my total number of points, and then I like taking a square root out of all that just so that the units are are the same as whatever I'm measuring distance in my plots. So if we take that, and again, oh, and I guess, what do we call this measure? This measure has a whole bunch of different names. It's called inertia because it is the same math as some forms of mathematical inertia. Distortion is possibly another one. So it's just like, if this was the ideal point, how much variability around is it? Or you can just think of it as loss. It's the thing that we would like this thing to be as small as possible. So all of those are legit names for it. And if we plot that, then we get this nice sort of, oh, hey, look, it gets better and better and better, and then it stops getting better. Normally with this algorithm, the point that it stops getting better, it's just no points are changing categories anymore, so no, the mean of all those points is going to be all the same. It's fine. The other thing that'll sometimes happen with this algorithm is it'll sort of, there'll be one point that's sort of like in the middle between two categories, and it'll like jitter back and forth between whether or not it's categorized in one group or the other group. In any case, pretty much always this will fairly quickly flatten out and then not get any better. All right. So there's a nice little clustering algorithm. What's some problems with it? A couple dangers to look out for if you're doing this algorithm. It's not guaranteed to converge to the best answer. That's sort of one thing. This is there are multiple stable solutions to this, all depending on what random order it's choosing points in, and the distribution of the data. For example, this data here, sometimes when I run the algorithm, I will get this as my solution. It will, all right, I've got one category for these two, one category that splits, and then two categories that split this one down here. That'll happen sometimes. Oh, sorry, I didn't actually show the animation. If I started randomly picking these three, then I just end like this, right? And it just stops and it iterates and doesn't go anywhere. So if you want to deal with that, so what you'll often do is just sort of run k-means a bunch of times, a couple times, 4 or 5 times, and then choose the run that has the smallest loss. Right? And that should give you a nice category. Okay, so definitely a thing to watch out for. Another issue that's going to come up, though, with k-means is that you, of course, where do you get k from? Fine, if I can look at the data, I'll tell you what categories are, but hey, if I can look at the data, then I don't need this algorithm to tell me what the clusters are. So something needs to tell me how to pick k. And with this data, if I pick k wrong, I'm going to get some weird results. So if I set k equals 2, fine, even ideally might get one cluster down here, and then one cluster grabbing these two, fine. If I set k equals 5, I'll probably get like a couple clusters that are split. All right. Or I don't know, set k equals 12, and we're going to have a whole bunch of little split things. Okay. How do I pick a good k? Again, so one thing we could try computing out of all these different things is, well, what's that loss value again as we vary k? Okay, 'cause this is, I said, this is the thing I want to minimize. Well, here's what that loss value looks like. And clearly what this indicates is, okay, well, we don't actually just want to minimize the loss, right? And sort of this makes sense, because if we wanted to just minimize the loss, if you wanted to minimize the distance, if you wanted to pick the k that minimizes the distance between each item and its prototype category label, well, then the best solution would be to set k equal to the number of data points I have. Have every single data point be its own category, which is not a very use, because the loss would be 0, right? That's not very useful. So we probably don't want that. So what people tend to do with this sort of thing is they tend to plot this, and then they go, oh, this here, that point there, that looks like a good number. Okay. This approach goes by a number of names. So I think most commonly it's called the elbow method, because you're looking at this sort of point that's kind of like an elbow in an arm. And of course, one interesting problem with this is you tend to do this by eye, because there's a whole, exactly defining exactly what this point is and figuring out a mathematical approach to pick this sort of point. It's a little bit tricky. There's a bunch of methods. You could compute the point of maximum curvature. Sometimes people do things like you draw a line from this point down to this point, draw a straight line across there, and then find which point on this curve is the farthest away from that line. Right, so that would be this point here. So there's a variety of methods there. But it's exactly which method you want. There isn't any particularly strong theory about exactly which method you want to use in there. It's more sort of, yeah, it'd be useful if I could have like 3 categories. You know, I'll try 4, try 2, try 5. Depends a lot on your situation. Okay. What else can we do? We should look at what happens to this algorithm when there isn't any sort of clear distinction between the groups. So if I have data like this, it still does a pretty decent job. Like, it still does something. Like, it gives me 3 categories: category 0, category 1, category 2. And just to be clear, these things that I'm plotting, so like this point here was the initial prototype, and then it moved to here, and then here, and here, and here, and here. This one here moved to there, and this one here moved to there. Okay. Normally you don't plot all of the learning trajectory, but just to give an idea of what that looks like. And really it does happen pretty quickly. It's like 10 iterations is all I was plotting here. All right. So it'll still sort of somewhat meaningfully organize that data. Again, whether or not this is becomes useful clustering depends a lot on what this actual data is that we're building. However, data isn't always very nicely organized. So, what is our algorithm going to do on this data? And this is sort of a little bit of an extreme example of, all right, I might, and I don't know, what, some weird situation, have data that looks like this. There's very clearly 2 categories of data there. It would be nice to automatically separate those out. What does k-means do on this task? Well, all right, so it started here and here, and then it ended up saying, all right, I got a prototype here that encompasses this group, and a prototype here that encompasses this group. Why is it doing that? Well, it sort of has to with this algorithm. This algorithm is assuming that the prototypes are sort of, there's a point, and all of the items in this category are sort of in that category in virtue of having some distance to that point. Okay. And that just seems clearly wrong for this sort of data. Okay. So this assumption that we're making that this sort of distance measure and being able to have one sort of ideal value for it, or one sort of ideal value, one ideal prototype, and just worrying about the distance to that prototype, that assumption just doesn't seem to hold for data like this. So this is an argument that for some types of categories, we're going to need something else. All right. So that's one issue that we're going to deal with in a moment, and that's going to be something that'll push us towards the sort of exemplar-based approaches. One other thing that we can deal with, though, and just sort of what's worth highlighting. So same data, same algorithm. This is kind of a weird solution that it's found. Well, almost the same data. I have changed the data slightly, and I've shown on the graph how I've changed the data, but I've changed the data slightly, and it's decided that it wants a prototype here, a prototype here, and a prototype here. What did I change to cause this to happen? Well, I very subtly changed this axis. So that data across, I just multiplied all the data on this axis by 100. And the reason I'm doing this is just sort of highlight, this is sort of a side effect of our distance measure. Right? Because we're using sort of Euclidean distance between points, and that's how we're saying how similar things are, that means that this distance here, which looks very big in this picture, this distance here, right? It's only a distance of, I don't know, from 2 to 7, right? That is a very, very small distance compared to this distance here, looking at our x-axis, which is like a distance between, like, I don't know, 600 and 650, right? What I'm highlighting here is whenever we're doing any of these sorts of distance measures, or any of this unsupervised classification, we're feeding a bunch of data in, and if the system is doing some sort of, I assume that whatever number is being fed in, there's something about similarity between these numbers that is telling me how I should group things or how things should be related. I've got to be really careful about what the scaling is. Okay? Because if my algorithm assumes the differences on one axis are, a difference of 1 on one axis is as meaningful as a difference of 1 on the other axis, then, if one of these if one of these values is, I don't know, price of vehicle measured in pennies, and on the other axis, so that's going to be values, numbers between 0 and, I don't know, 100,000. So whatever, having a very large range on one axis, and if the other axis is, I don't know, the weight of a vehicle measured in tons, then that's going to be a very small range. It's going to be a range, plus or minus 1. That if you feed that sort of data into your algorithm, it's going to say, oh, okay, differences in price of 1 penny is as important as difference in weight of 1 ton. Okay? Which may or may not be what you want. Probably is not what you want. Most of the time, people will try to avoid this problem by doing something like normalizing their data before they feed it in. Okay? Just to sort of give everything the similar range, and that's just sort of like just a null assumption of just simply saying, look, I don't know what's going to be important here. Let's just assume everything's equally important. If you do know something about your data, you might scale things differently, but a lot of times that's the sort of the default that people will do. Cool. All right. Yay, k-means. Let's do, okay, so that's sort of a good, solid, canonical prototype-based approach. Let's do one that's focused much more on the individual items themselves, and that are trying to build up a category out of, here's the set of examples that are elements of this category, okay? Rather than trying to build up sort of, oh, here's one canonical version of this category. All right, so what are we going to do here? Same data. What do we want to do? Well, if we want to do something really focused on individual items as being sort of examples of a category, let's start with that extreme example I said of every single item is its own category. Right. So I've got 200 data points here, I've got 200 categories. And that's, as I said, it's like, okay, well, this is a really useless structuring. So what I'd like to do is reduce the number of categories. Well, let's do that the simplest, like, well, what's the easiest thing to do? Well, let's say I just want to reduce the number of categories by 1. I just want to get rid of 1. What I could do is I could find the 2 points that are really, really close. Whatever 2 points are the closest, and probably those points. I don't know. There's going to be 2 points somewhere in there. There's 2 points that are the closest. Let's take those 2 points and say, all right, okay, you two are now the same category. All right. Now let's do that again. And then do it again, and do it again, and do it again. We got to be a little bit subtle here in that at a certain point we're going to be like needing to say, okay, well, I have one category that has 2 dots in it, and I have another category that has 2 dots in it. How close are they? I need some way of defining that. Again, variety of ways of doing that. Sort of the simplest is, look, the distance between 2 categories is just the closest distance between any 2 points within those categories. Okay. If I have, I don't know, if I have a point here and a point here, and then I have a point here and a point here for the other category, then the closest distance is that distance between the point in this category and the point in this category that are the closest. Okay. All right. What does that do? Okay, so here's some data again. Colored each one. Well, there's probably some repetition in color there, but everybody's in a different category. And I'm going to start merging. What I'm going to plot over here on the right is how many clusters I'm at right now. So it looks like I've already merged a couple of them, because I've got 200 data points here. But then the y-axis is going to be that merge distance, what that distance was between the 2 points that I merged together. And it's starting off very, very small, and then it should gradually increase. So I merge a bunch more clusters. I've now merged, so okay, so you can see all of these have now sort of merged into one cluster. Looks like those have also merged into one cluster. And we keep doing that. Ooh, okay, these ones are all sort of nicely merging together into one cluster. Right. One cluster, that's a cluster. These are starting to go out. That one's starting to all sort of merge together. Keeping on adding things. We're now down to 5 clusters, I believe. So we've got there. Looks like that is in one. Not sure where the other data point. Okay, maybe 4 clusters. And actually 4 isn't too bad for this one. Maybe you do leave this one just on its own as a separate cluster. That might be perfectly reasonable. I can go up to exactly 3. And then of course I could keep going, and now everybody's part of one cluster. And again, you can sort of look at this sort of graph and say, yeah, maybe somewhere around here is a good choice for the number of clusters. Okay. Although one nice thing is once you've gone through this process, I can just, as long as I've sort of stored that data, I could pull this bar back and say, I don't know, I want 100 clusters, I want 50 clusters, I want all sorts of things. Right? So it does all of the groupings for you. Okay. Cool. All right. It's an algorithm. Unsurprisingly, it works beautifully for this data. This that the k-means exactly failed on. Right, so again, reminder, if I go back to the k-means on that data, oops, there it is, wildly wrong. Right, and this is sort of the perfect example of data that this hierarchical clustering would be absolutely perfect for. Right. So again, this is what it's meant to be able to do. Had some nice features. So one interesting side effect that you can sort of get. So okay, one of the things that people do often when you've got this sort of hierarchical clustering, it's called hierarchical just because we're clustering and then clustering and clustering and clustering, is you can actually plot that process. And so that's what I've got here on the right. What I'm plotting down here is these are all of the original sample points, and I'm just sort of plotting what index they are as opposed to their XY values. And what this is plotting vertically is that merging process. So the first thing that happened was these two got merged together, because this is the smallest merge distance. Okay, so those two got merged together. Then those two got merged together. Then those two, then those two, then those two, etc., etc. Right, it's sort of vertically up. And then through that process, you can then look at this diagram and say, okay, oh, nice. So this is when those two big clusters got merged together. Or sorry, if you continued the process and merged them all into one giant cluster, this would be combining those two. Okay. On the left here is one of these two curves, and on the right is the other one. Okay. And then you can sort of see, all right, there's some grouping here, and then a grouping here, and that's sort of sub-chunks of this curve that happen to get merged together. Okay. So this becomes a way of like looking for, of visualizing structure in your data. And with this sort of one, again, there really isn't much structure in the actual data itself, but we can at least see this sort of fairly clear split down the middle of that. Okay. And the fact that there's many merges that happen here sort of indicates, like this split and this split probably weren't important. But if you anytime you find a big space in distance where there's no splits, that seems to be sort of, okay, here's an important division. Okay. All right. So that's just, again, something you can do anytime if I have data, any sort of raw unstructured data, I can throw this algorithm at it, and it can at least do this sort of clustering. Okay. Same issues are going to come up as with the k-means in terms of things like, oh, make sure your data is normalized. Well, again, if I took all of x1 and multiplied them all by 100, that would change how this clustering happens, just because it changes what distance means. So we can get these sorts of structures. There's one other fun thing we can actually do with this diagram, because one thing this diagram has done is it's kind of given us a way of ordering these data points. Right? I now have, like these were just sort of randomly generated data points, and now I can do sort of an ordering on them. And so if I take that same plot and use it to sort of color the data points, you can sort of see the clusters, the subclusters as well. Right? So you can see, okay, so what it did is it grouped together this chunk, so that's, this part over here, probably that part over there, things like that. You can see all these sort of things being built up. It's not a perfect smooth sort of ordering of these data points. I mean, it's hard to define exactly what the best ordering of these data points is, but it is an ordering of these data points that's at least not horribly wrong. There are algorithms and options to sort of, hey, swap the order, of which order you put these two in, these two data points in, because they're sort of when they're grouped together, they're put in a random order, which one's on the left and which one's on the right. But you can adjust the algorithm a little bit to sort of swap the order such that this across here, or it tries to minimize the distance between points in order across. And that'll do a little bit of a better job of sort of ordering these points in some sort of meaningful way. Why might you want that? So this is a situation, I've got a bunch of data points I want, and not only am I getting sort of, find me any structure in the data, I might, what I'm saying here is, okay, put them in some sort of order. Where points that are near each other, or sort of next to each other in that order, have similar value. I guess that's one way to phrase what I'm trying to do there. This is actually something that I've used somewhat regularly in my own research in sort of a weird situation. So just to give a particular application where I have found this particular algorithm handy, what you're looking at here is data from a simulation of neural activity in some task. And in this particular neural simulation, so time is across the x-axis here. What you're seeing are the outputs from 100 neurons. Neurons in simulation, and most of the time in biology, the output of a neuron is normally nothing at all, and then every now and then the neuron emits a spike. Okay. So what you're seeing across here is like, okay, this neuron up here, neuron 100, did nothing, 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 and then went, oh, it emitted a spike at this point, and this point, and this point in time, and at this point in time, and then it was quiet. And then the next neuron did something else, and the next neuron did something else, the next neuron did something else. And this is somewhat typical data for me to be sort of staring at and go, okay, what in the world is this neural activity doing? What does it mean? Indeed, neuroscientists will also look at this sort of data from real brains. They'll do some task. They'll, I don't know, give the turn a light on for a rat at a particular point in time and measure the neural activity around then. What I would like to do, and I'm just measuring from all these neurons, this looks like a mess and I can't read it, and I'm not getting anything at all from this other than the neurons seem to change their activity a lot and I don't see any patterns. So this might be a situation where it might be handy to reorganize these neurons so that similar ones are next to each other. And so one thing I could do is do exactly the clustering algorithm I just talked about, but so I've got 100 data points, and the values that I'm going to do the clustering on are exactly this big giant long vector of 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. Big giant long set of numbers. That's what I'm going to use for each of my data points, and then I'm just going to use the clustering algorithm that we just saw. One slight change one slight thing I want to be really careful on, since I want my distance between points to be somewhat meaningful. If I've got one data point that was all zeros, these three little ones right here, and that little one there, and then all zeros. If I have one neuron that does that, and I had another neuron that, say, did exactly the same thing, but, I don't know, each of the little bits of neural activity was like 1 millisecond later. Well, if I just did sort of a normal dot product, and if I just sort of did the Euclidean distance between those 2 points, then that Euclidean distance is going to be just as big if those things were 1 millisecond later as if they were like wildly different. So like if one of them had 4 spikes here and the other one was all zeros and just 4 ones down here. All right. If you just go ahead and do a strict sort of Euclidean distance between those 2 points. what I do instead is then I say, okay, well, fine. I want, if there's values that are sort of nearby each other or similar points in time, I still want that to be kind of similar. And so what I do is I sort of take this data and then blur it a little bit. So just sort of I just convolve it with a Gaussian, or pass it through just some sort of blurring image filter, so that data is blurred this way. And if it's blurred that way, then now all of a sudden, as long as values are happening at similar points in time, all right, they'll still have a fairly high distance between the two when it computes the distance. Or sorry, small distance between the two when it computes the distance. Okay, sorry. So slight caveat in there, but again, this is about making sure your distance measurements are meaningful. If I go ahead and do that, and I take this data, I do that clustering, and then I put them in order. If I do that, I get this. Okay. Reason this is sort of useful is like, okay, now we can look at this. Oh, okay, look, there's a bunch of, I turned the light on for the rat at this point in time. So neurons were doing something. Some neurons were not doing anything beforehand. Some neurons were being active. I turned the light on at this point in time. So there's some of these neurons that were not active here, or sorry, that were active here, become not active about 200 milliseconds later. Right? I get other neurons that I turn the light on, they were not active here, and they start being active pretty soon right afterwards. I get other neurons, light turns on, pretty much nothing happens, and then there's a group that turn on sort of later. This is a way of at least pulling out, or like sort of quickly organizing my data, and the only thing I've done is change what order I'm plotting these things in. And it makes it a little bit easier for me to pull data out, or at least see sort of patterns in the data. All right. So let's follow up on that a little bit more. So this idea of, I don't just want categories. What I'd really like those, I might have sort of, I want to do something about organizing the, figuring out other ways of organizing the data. Maybe that's how I want to put it. So one way to phrase that is, what if we want our categories to have some structure? So I want a category. So let me do back to a counter example here, all the way back here. There we are. So in this one here, I have three categories: category 0, category 1, category 2. And what we've got here is, this is category 1, this is category 0, and this is category 2. And that's a little bit weird. Like, what I probably want is, I'd like to swap them around. Like, it should be like, well, this is category 0, then category 1, then category 2. Or the other way around, category 0, category 1, category 2. This should be the middle category. All right. And that's not something that K-means is trying to do. There's no sense of order to these. It's just to order to these prototypes. It's just, hey, I have 3 prototypes. Please spread them around. If I want some sort of interesting structure in my data, I might want to say, hey, look, I want category 1 to be somewhere in between category 0 and category 2. Right? So I'm going to impose extra structure on this data. All right. Of course, if I'm going to do that, I'm going to need to be able to define, hey, look, for each category, which are the ones that it's supposed to be similar to, and how similar is it? For some quick examples, so, okay, this seems, why would you want to do this? I will note there's lots of sort of handmade, human-made categories that do exactly this. So the categorizing the vowels in human language, if you go look, they don't just say these are the vowels, they also organize the vowels and say, hey, look, there's structure here. These are the vowel. So this particular vowel is more like this vowel and more like this vowel than it is to this vowel over here. That's the sort of thing we're capturing. Another example, here's how you classify sand, clay, and silt. There's just sort of organizing where I've got categories, all right. But silt is more similar to silt loam than it is to clay. Okay, and I want to sort of maintain this category. So I'm just doing those as examples of when people make categories, they often want structure in those categories. So how are we going to do this? Well, we're going to do sort of a variant of the k-means. And this is called a self-organizing map, also sometimes called a Kohonen network. We're going to start exactly like k-means. We're going to choose a random set of prototypes for categories. We're probably going to choose a lot more categories. Okay, we're going to have, we'll have more categories, or choose a fairly large number of them. We're going to define some structure for those categories. So are these categories, say, organized on a line? Are they in a grid? Are they a three-dimensional grid? Are they some triangular structure? Whatever structure I want. And that structure is sort of saying, if I have one particular category, which other categories is it similar to? So we only have the structure in order to allow us to define some distance between these categories. Now to update what those, so again, we're going to randomly choose our prototypes, and then we're going to do some update. And the update that we're going to do is we're going to randomly pick an input data point. Okay, and we're going to then categorize it, determine what category that's in. Then, sort of like with the k-means, we're going to move whatever category it's in. Fine, we're going to move that category's prototype a little bit closer to this point. Okay, it's sort of like a tiny iterative version of what we did with k-means, which was just, all right, take all the points that are in that category and just take their mean. We're just doing this one point at a time. So all we're going to do is we're going to slightly shift that prototype towards our new input value x. But then what we're also going to do, so we're moving that category's prototype towards x. We're also going to move the nearby categories as well. And by nearby, I don't mean other categories this point could be in. So when I categorize the point, I say, all right, this particular point x, this is the, I find which of all the categories is it closest to. Fine. But I'm not saying choose the one that it's closest to and the one that it's second closest to. That's not what I'm meaning here. What I'm meaning is the category that it's closest to and those categories that are close to that category in this sort of structure that I've said. And we're going to start with a large nearby neighborhood. And then we're going to gradually reduce what we mean by nearby. Okay. So if I've got, say, categories in like a 5x5 grid, and there's one particular point in the middle of the grid that says, oh, this is the prototype that I'm closest to, I will move that point towards x, but I'll also move, say, the 4 neighbors of that point towards x. Often what we do, instead of like the 4 neighbors, it's more sort of, all right, what's this math say? This is, so, to attempt to quantify what I'm saying there. So CI, that's the prototype for that particular category. Okay. And how am I going to change that? The amount I'm going to change that particular category. So I'm going to, I is that just iterates over all the categories. Alpha, that's some learning rate. So fine, that's how much I'm going to do that. Let's ignore this giant block here for a moment. X minus CI. So X, that's the new point that I'm testing. X minus CI. All right, if we ignored this whole big giant thing here and assumed it was 1, then what this update rule would say is move CI towards X. because so move my category towards X. So that's what we're doing for whatever, move the category's prototype towards X. So X is in some category. That particular prototype should get moved towards X. So we're saying X minus CI, that's the difference between X and that category. And then we're going to scale that a little bit. That's what we're going to update. That's for the best category, for the category that is the closest match for this input. What this thing here is doing is saying for all the other categories, what's the distance between that category and the best category? Notice that this has nothing to do with X. This is just the distance between the categories. So if all my categories are on a big grid, then it would be the distance in that grid. And whatever that distance is, fine, square it, divided by 2 times. So this is the Gaussian equation. So for if I is the category that I'm best at, the distance between the best and itself is 0. E to the 0 is 1. This all turns into 1. For every other category, it's going to be some value that is less than 1. Okay, so other points are going to get slowly moved. And then we start sigma at a large value, and then we gradually decrease it. All right, that's hard to follow. Let's actually try doing this as an example. Here's some data. And I've got 25 categories, and I'm going to arrange those categories on a line. Okay. And I'm going to randomly assign each of those categories a prototype. And I'm going to get this horrible mess here. Right? And what I'm doing here is I'm drawing all of the prototypes, but then I'm drawing lines between them in order to say who's connected to what. So prototype, this is the first prototype, and then this is the second one, and then this is the third one, and this is the fourth one, and that's just a big giant mess. Right? Those prototypes are not in any order. I do one iteration of this algorithm by just going through every single data point in the data set and doing that algorithm on it, and I get this. Okay? These are my prototypes. They're already in some really nice sort of order. Okay? They're not quite matching the data yet, but they're getting there. I do it again, do it a few more times, do it a few more times. And now what I have is these categories all sort of lined up. Okay? So this is a way of taking the prototype, so I'm not just simply saying, hey, find me 25 categories. Find me 25 categories that are organized in some sort of meaningful order. All right, so that's an interesting option. What things can we do with this? I definitely want to point out that there's sort of 2 ways of plotting this data. So one thing I can think of is, all right, where are those categories in this x1, x2 space? So right? But then what I could also do is I could just plot those 25 categories. So those across here, these are my 25 categories. And what I've done is colored each category by what this xy value is. I'm just using red and green. So one of these axes defines how red it is, the other axis defines how green it is. Right? And you get this sort of nice, smooth representation of this data. Okay. Again, if we had sort of more complex data, I don't know, these are a bunch of pictures of different things, and then we might they might be all sort of smoothly grouped together now, such that we're sort of gradually going from, I don't know, pictures of cats over here to pictures of dogs over here, and sort of some sort of intermediate smooth sort of cat-dog things in the middle, or whatever. Real-world data is a little bit smoother than that. One-dimensional isn't all that common for this. What's more often is people are using this for two-dimensional, because this becomes a general method for taking data of any sort of dimensionality, and whatever data we're feeding in here, and saying, hey, take this data and plot it for me in 2 dimensions, which is useful because it's very hard to visualize things in more than 2 dimensions. If I want to sort of draw things as a picture, then I want them as sort of 2 dimensions. That's sort of the most common thing that a self-organizing map is used for. It's why it gets called a map. And so one particular example is I might want to take, say, colors, just to pick something random. So that's three-dimensional data, and it's completely unstructured three-dimensional. It's just all combinations of red, green, and blue are possible colors. It's not totally unstructured, but I don't know. Maybe if you had a picture or a set of real-world pictures, what particular colors are most common, or something like that. That's but for this purposes, I'm just going to randomly generating three-dimensional data, red, green, blue sort of colors. And I'm going to say, all right, please shove those into a two-dimensional map. And if I start that algorithm and I just randomly initialize those prototypes, well, okay, so my map is a 25 by 25. So I've got 25 times 25 prototypes. I randomly generate them. That's the prototypes. This is a horrible mess. But then I run this algorithm, and I get a nice sort of smooth, oh, okay, all the yellows here, I've got the whites, black, I've got a smooth way of organizing this data. And again, data that's similar to each other, so data that's similar to each other in the original space, the original three-dimensional space, the color spectrum space, are plotted to be similar to each other on this two-dimensional space. It's not going to be perfect. It can't be, because I'm taking three-dimensional data and I'm shoving it into 2 dimensions. But it's a nice technique for visualizing any data you have in 2 dimensions. You'd have to be a little bit careful. Certainly, as if you do it with a very large sigma, so a very large neighborhood, you'll get something like this. You do it with smaller, then you might have things might be a little bit more clustered. Maybe you want that, maybe you don't. But certainly you'll get perhaps a little bit more repetition if you start with sort of a smaller neighborhood. One final thing I'll just say about this, again, coming more from the trying to understand the brain perspective and trying to, is this something that actual intelligence needs to do? Interestingly, it seems to be a really good match for some things in biology. So what I'm plotting here is some data taken from the visual cortex of cats. And this is the actual sort of, so on the right here this is sort of an actual data measuring neurons in the cortex of a cat. And then what we're doing here is the little arrow. So they are showing bars that are rotated at different orientations and moving across the visual field of the cat. Right. And what we're plotting here is, for each point in the cat brain, they gave it a bunch of stimuli and they figured out, okay, what is the thing that causes these neurons to be the most active? And the color indicates the orientation of the bar, and the little arrow says what direction the bar was moving in. And so this is just, all right, let's go ahead and measure this data. And you get this interesting phenomenon that neurons nearby each other, so nearby points in the cat's brain, end up responding to somewhat similar directions. And somewhat similar directions, and somewhat similar orientations. And if you take exactly that same data of a bunch of my data is just a bunch of orientations and a bunch of directions, and I do exactly that self-organizing map algorithm on it, I can get some pretty similar patterns. So on the left there is what happens with a self-organizing map, given that sort of data. Again, you get this sort of nearby similarities. You get these similar sorts of interesting pinwheel patterns here, where all the colors sort of come together. Right, so one of those, sort of similar to one of these. So there's something about that sort of organization that at least some parts of biology are doing. All right, that's enough of that. Summary for all of today. If you have just a bunch of data and you want to organize it somehow, have some ways of automatically finding structures in the data, here's at least some basic techniques. K-means, just find me 5 K prototypes that best capture the data. Let me know what those are. Hierarchical clustering, just sort of start grouping these data points together, see at what point how those groups form. And then if there's some sort of organization that I want on those prototypes, I can use self-organizing maps. For all of these, the distance measurement matters a lot. Normalize your data before you do this, or scale it if you think certain dimensions are more important than other ones, and scale those ones to larger values. The use of these things ends up being sort of giving you tools for digging into some data, if at least lets you sort of start somewhere. One sort of caveat with all of this is all of the algorithms I just described have tons of variations, and it's really hard to know what's best for a particular data set, and often you just sort of try some things out and see what happens. All right, so that's our dive into unsupervised learning. We'll come back to unsupervised learning later in the course. I do think most of this course will end up being at least somewhat supervised data. But these issues will come back and haunt us in the future. But there's a couple places where you can just do that, even with all you have is unlabeled data. Thank you very much. We'll see you in the next class.